Hello everyone. Let us deal with something called as RSA algorithm today. RSA algorithm is actually an asymmetric key crypto system where a public key is used for encryption and the private key is used for decryption as usual. RSA stands for Reves, Shamir and Adelman, who are the three guys responsible for this type of crypto system. We still use this type of crypto system today in our encryption processes like HTTPS, etc. So let us look at this crypto system step by step in three steps. Step number one, which is a description of public key and private key. As you can see, the public key is a combination of two different keys, two different numbers over here. The first number is a product of two huge primes. When I say huge, they are up to 200 to 300 digits in the real life. But for our convenience, we will go for a smaller product of primes. Let us say we can choose our P as 3 and or Q as, let's say, 197. You can check that 197 is also a prime. So I write my N as 591 in my case. The next number is called as the encryption exponent. Encryption exponent. The condition for the choice of this encryption exponent is that it should be co-prime with phi of n. Now what is phi of n? If you remember, phi of n in our case is P into Q, and the formula for the Euler's phi function of such a product of primes is nothing but P minus 1 into Q minus 1. And also remember one fact that you can find this phi of n only if you know what your P and Q is. That's what the formula says. So if a hacker wants to hack a message and calculate the D, which actually depends on phi of n, the phi of n can be calculated only if you are able to factorize this n into the product of two primes. And let me tell you, in even in the today's world, with the modern technology that we have, it has been estimated that the quickest factoring algorithm known can use approximately 1.2 times 10 raised to 23 computer operations to resolve an integer with 200 digits into its prime factors. Now, assuming that each operation requires, let us say, even 10 raised to minus 9 seconds, which is 1 nanosecond, the factorization time for such a 200 digit number would take around 3.8 multiplied by 10 raised to 6 years, which is huge, and it takes less than a second for a message to get transferred today. So nobody is gonna wait for that long. Okay. So now let us look at the encryption exponent. In our case, let us take 3 as the encryption exponent here, because 3 is co-prime with phi of n. Let's first calculate this phi of n. Phi of n is going to be 3 minus 1 into 197 minus 1, which is 2 multiplied by 196, which is nothing but 392. Okay, and you can very well check that this 3 is co-prime with the phi of n that we have. D is nothing but the inverse of this encryption exponent. It's called as the decryption exponent in our case, because it's used to decrypt the ciphertext. This D needs some calculation, which I will show you later. So this is the private and the public key. What is the encryption process? The encryption process, every plain text which when raised to the encryption exponent gives you the ciphertext. In our case, the encryption exponent is 3, so I raise my plain text to the power of 3, modulo n, which is 591 in my case. So let us say, for example, if I want to encipher or encrypt the message H, whose numeric equivalent is 7, I will go for the formula C congruent to 7 raised to 3. Now 7 raised to 3 is 343, and this is all being done modulo 591. So this is the ciphertext equivalent of the plain text that we have, that is H. Now let us look at the decryption process. The decryption process uses the formula P congruent to C raised to D modulo N, which means that if you raise the ciphertext numeric equivalent to the power of the decryption exponent, you get the plain text back. Now the thing is, how do you get this decryption formula? You can skip this part if you want and go ahead, because this won't be required while you will be solving problems based on RSA algorithms. Okay, so let me explain you how you get this. This is obtained using the equation number 1, which is the encryption formula. So the encryption formula is C congruent to P raised to E modulo N. If you raise both sides to the power D, you will get C raised to D congruent to P raised to ED, C raised to D congruent to P raised to ED modulo N. Remember that D is the inverse of E modulo N, which means that D times E or E times D is congruent to 1 modulo, it's not modulo N, it's modulo phi of N. So E times D is congruent to 1 modulo phi of N, which means ED is actually equal to 1 plus some integer multiple of phi of N. This, when substituted over here, it gives us P raised to 1 plus K times phi N modulo N. Now, if you use your basic law of indices, you will notice that this is nothing but P raised to 1 multiplied by P raised to K phi of N modulo N. Now, this P raised to K times phi of N can be written as P raised to phi of N, the whole raised to K modulo N. Now, it's very obvious that this P raised to phi of N is nothing but, this is nothing but P. This is nothing but P. But this P raised to phi of N is actually congruent to 1 modulo N, the whole raised to K. Why is it so? If you recall, there is something called as Euler's theorem, which says that P raised to phi of N is congruent to 1 modulo N. This is all provided the GCD of P and N is 1. So you clearly get your decryption formula using this. So C raised to D is nothing but P modulo N. Okay. Now let us go ahead and use this decryption formula to get our plain text back from the ciphertext numeric equivalent, which is 343. I will have to raise this 343 to the power D modulo N to get my the plain text back. For that, I will have to calculate what my D is. I already know what my phi of N is, which I had calculated before. It was 392. To calculate my D using the E, I use something called as Euclidean algorithm. So how do I use this Euclidean algorithm? How do I find that D, which when multiplied to your E, which is 3 in our case, gives you 1 modulo 392. How do I do that? Okay, so I need to divide 392 by 3 and do this repeatedly till I get my remainder 0 or 1. So let's see. 3 times 130 gives you 390. So this is 390. Now in a Euclidean algorithm, you make the previous divisor as the dividend and continue the process. So 2 into 1 gives you 2 and then gives you the remainder 1. Okay. Now using the division algorithm, I know that this 1 can be written as 3 minus 1 into 2. So this is 3 minus 1 into 2. Again, using the division algorithm, I can write this 2 as 392 minus 130 multiplied by 3. So I can write this as 392 minus 130 into 3, What does this give me? Let's check. 3 minus 1 times 392 minus 1 multiplied by this gives you plus 130 multiplied by 3. Combining these two guys gives me 131 multiplied by 3 minus 1 multiplied by 392. Okay. Now, if I take the modulus of both sides, modulo 392, you know that this disappears because it is congruent to 0 modulo 392. And I have the inverse of 3, which is 131. So my D I have found out to be 131 modulo 392. Okay. Now I can decrypt my ciphertext. The formula, if you remember, was P congruent to the ciphertext raised to D modulo N, which was 591. Yeah, 591. So the C, what was the C here that we have found out? C was found out to be 343. Let's write that C over here, 343. And the D we have found out is 131. And this is all happening modulo 591. This number may appear very huge to you, but remember this 343 was nothing but 7 raised to 3. The whole raised to 131. Which is nothing but 7 raised to 3 multiplied by 131, which is nothing but 393 modulo 591. Again, using the law of indices, you will notice that this is nothing but 392 multiplied by 7 raised to 1 modulo 591. Now again, 7 raised to 392, if you remember, is nothing but 5 of 591. And again, using the Euler's phi function, Euler's theorem, this gives you 1 multiplied by 7, which is 7 modulo 591. And hence, your plain text is 7, which was H, as we had started with. So this is the RSA algorithm. To sum it up, let me show you again. RSA algorithm, as usual, consists of 3 steps. First step is about the public key and the private key. The public key uses a combination of 2 numbers. The first number is a product of 2 primes, and the second number is called as the encryption exponent, which is co-prime with phi of n. The private key here we had found out later to be 131 is something called as a decryption exponent. It is the inverse of the encryption exponent modulo phi of n. It's not modulo n, it's modulo phi of n. This is what you have to remember. The encryption process is this. A ciphertext is congruent to the plain text raised to the encryption exponent. That's the reason it is called as the encryption exponent. Everything else is in modulo n, except for this, except when it comes to the exponents. And the decryption formula is the reverse of that. It is P congruent to C raised to the decryption exponent modulo n. This doesn't need to be done when you're solving a problem. And then to calculate D, we use Euclidean algorithm as usual. And then you find out your D. We have found out our D to be 131. Substitute here in our decryption formula, and then finally obtain the plain text, which is 7 in our case. Thank you so much for listening.